Alright, what's going on everybody? In this video, we're going to be talking about limits and continuity. More specifically, I'm going to start off with this video just by defining what continuity is, right? We're going to talk about that because if we don't know what continuity is, then everything that comes after this is just going to be really confusing, and I'm not trying to have that for you. The next thing that we'll talk about, we'll just go through finding different discontinuities. That'll be pretty quick there. I just want to do like a few examples, and then we'll talk about some theorems of continuity, right? And the theorems that we'll talk about are pretty crucial to understanding the practice problems that will follow. Okay, and those practice problems will be what we do next, followed by talking about continuity from the left or from the right, right? You can have like one-sided continuity, just like you can have one-sided limits. And then we'll finish off by talking about the intermediate value theorem, which kind of gets roped in when you talk about continuity. It's interesting, kind of, but you're not really going to see much of that on like a quiz or a test, really, in my opinion. Anyways, that is the scope of what we'll be doing in this video, and as a quick reminder, I do have my full Calculus 1 course in the description down below that I definitely urge you to go check out if you want plenty more practice problems to go through with me, and it just gives you a better way to reach out to me. We can talk one-on-one about anything that you're having trouble with the Calc 1 course, and it's just it's a much better chance for me to get to help you. So if you're interested in that, I definitely recommend that you check out the description down below. Now let's hop into this video. So starting off with the definition of continuity. So as an example, just starting off with talking about, what does continuous mean, right? Well, y equals x squared is going to be continuous for all x values, right? And that means that at every x value, this graph is going to have a corresponding y value, right? So it's never going to stop, right? It just continues on, right? There's no like holes, or it's not just like something like this, right? Or anything like that, right? It continues on. There's no stops, okay? And that's what continuous means. Now that's not the same. That's not going to be true, right? For this function right here. Right? With this function, we have a x minus 2 in the denominator, and what that ends up meaning is that, well, at x equals 2, we're going to end up with a discontinuity, right? We get a 0 in the denominator here, and so we don't get an actual y value for that, right? So there's no point at x equals 2, okay? And so this function is going to be discontinuous at x equals 2. Right? It will be continuous everywhere else, right? But at x equals 2, right, we come in, maybe it's a hole, or maybe it is something like this, where it like does like an infinite discontinuity, right? So that there's different types of discontinuities that you can get, but the whole point is that that is something that you would call discontinuous at x equals 2, because it's not just continuing on, it's getting stopped. Awesome. So now that I've just talked you through the basics of what continuity is, let's get a little more difficult, a little more rigorous with how we talk about this stuff, right? Let's get a little more mathy. And so what we're going to do is we're going to use limits to define what it means for a function to be continuous at x equals a. Now, for a function to be continuous at some x equals a, right, some a value, or some x value rather, it's going to be continuous if the limit as x approaches a of f of x equals f of a. Okay? So what that means is that the point that you're dealing with, right, f of a, needs to be equal to the limit from both sides as x approaches a. Right? That means that both parts of the curve have to line up at the point. Right? Because the lines around the point are what we talk about when we talk about limits, right? We talk about, where this line is going, where it's approaching. And the point itself is, well, the actual f of a, right? The actual, x coordinate that you're plugging in. So hopefully that makes sense. Like when we talk about limits, right? We don't just like for instance, it would be discontinuous if the limit did not equal the actual point. Like maybe the point's up here, but the limit says the point should be down here, right? Or it says that that's what the curve is approaching, is a point down here that doesn't actually end up existing. Okay, and especially too if the limit doesn't even exist in the first place, right? This thing isn't going to be continuous, right? Here the limit from the left side, from the negative side, is not the same as the limit from the positive side. All right, moving on to our next section on finding discontinuities, right? I have an interesting practice problem here. Let's find if the following function is discontinuous at x equals 2. Okay, that function is, I believe, the same rational function that we had before, right? Rational function meaning it's a polynomial over another polynomial. That's something that you talk about quite a bit in Algebra 2, or whatever math level you're in. If you're in like if you don't have like an Algebra 2, whatever. Anyways, so this is for x is not equal to 2, right? Because there's a discontinuity there, right? And we already talked about that. But we want to see, well, does this point that we add in to this function for x equals 2, does that replace the discontinuity from here, right? In other words, maybe we have some curve and we get an open circle, right? We don't get a point there at x equals 2. Right? But this might be at y equals 3. And so when we have this piece in here that we also add into this function f of x, it plugs it, right? And so that's the gist of this problem. So what we want to see is, well, does the limit as x approaches 2 of f of x equal f of 2, right? Well, let's think about that first. Well, what's f of 2? Well, if you plug in 2 right into this function, what do you end up getting? Well, if x is equal to 2, we get 3. It says that in the piecewise function. So this is 3. Now, let's talk about that limit as x approaches 2 of f of x, which is equal to the limit as x approaches 2 of x squared, minus x minus 2 over x minus 2. And just because I realized I have the lines on here, I'm going to turn those off. I don't know. Some people like the lines better, some people don't, and I don't know. I think I like the lines off. All right, so we can factor this, right? Just to see if maybe we, just to figure out how we can actually evaluate this limit. See if we can get some cancellation with the term down here. And if we factor this, well, what are two numbers that add to be -1 and multiply to be -2? Let's think here. We could do -2 and +1. And there you see that we get the x minus 2's that cancel. And we end up getting the limit as x approaches 2 of x plus 1. And when we plug in 2 for x here, right, that's something we can just do now. We can plug in that 2 for x. We just get 2 plus 1, and that's 3. And so what we end up seeing here is that, well, f of 2 equals that limit, right? So this is true, and therefore the function is continuous at x equals, and remember we substituted in 2 for a here, right? So the function's continuous at x equals 2. Okay, so I'll write that down. My handwriting looks awful right now. Okay, so the function's continuous at x equals 2. Remember what that means, right? That means that we have our graph coming in here. It's got an open circle, and since we defined a new point here at that point of discontinuity for this function, well, that point actually ends up plugging it, right? And we figured that it plugs it by just evaluating what the limit was and seeing if it was equal to the y value of that point. So moving on to the next section, we're going to talk about the theorems of continuity. Now, remember that these theorems, right, they are going to be extremely important for the practice problems that we're going to do, okay? And the practice problems that you will see, right, you're going to have to think about these theorems, right? And they should just be something after we go over them, that should just be kind of in your head. It's not something like any theorem that you have to write out every time, but you'll see what I'm talking about. So the first theorem that we have here is that if f and g, just two different functions, right? If they are continuous at a, okay, they're continuous at some x equals a, right, some x value, and let's say that c is a constant, okay, then the following functions are also going to be continuous at a. So if we add these two functions together, we'll still get something that's continuous. If we subtract these two functions, we'll again get something that's continuous. If we multiply one of these functions by a scalar, right, by just like some constant c, like a 2 or a 3, it's still going to give us something that is continuous. If we multiply them together, we get something that is continuous. And if we divide them, we'll get something continuous, provided that your function isn't going to be 0 in the bottom. Okay? So, as an example, right, is x squared plus x plus natural log of x continuous at x equals 0? Right? Well, let's think about it. Okay? This theorem, theorem 1, is telling us that we can, we just have things being added here. We have different functions, right? And so we can just look at each individual function here. We can look at x squared. Is that continuous? We can look at x. Is that continuous? And so we can like piece it up. So let's answer that. Is x squared continuous? Well, at x equals 0, I mean, x squared is continuous for everything, right? So we can write yes, right? And the same with x, right? Yeah, of course, x is going to be continuous everywhere. Okay, there's no points of discontinuity. There's no points where you don't get a y. Okay, but natural log of x. Plug in x equals 0, and you get natural log of 0. That's not going to be a valid point, right? Natural log of 0 doesn't exist. And so that's going to be a no. And so since that is not defined at x equals 0, that means that the entire function is not going to be continuous at x equals 0, because there's no point there to begin with. And so the answer is going to be no. Okay, and remember what theorem, or what part of the theorem were we drawing from? The first piece. Okay, we were saying, for f plus g to be continuous at a, f and g both need to be continuous separately, right? So that means that, x squared, x, and natural log of x all need to be continuous separately at x equals 0 for their sum to be continuous at x equals 0. Hopefully that's not too confusing. Moving on to our second theorem here. This is just a little quick one that is nice to know. The following types of functions are continuous at every number in their domains. Okay, so these are the functions that are going to be continuous everywhere. Now you've already probably guessed that polynomials are going to be continuous everywhere, right? There's no parts where polynomials are going to be discontinuous, right? Rational functions are going to be continuous in their domains, right? Meaning that it matters what your domain is, right? So if you have that x minus 2 in the denominator that we had before, right? Well, that rational function is not going to be continuous at x equals 2, right? Unless you have some piecewise function and you're plugging the discontinuity like we did in the orange section. Okay, so that's a rational function. You also have root functions, right? Again, we're talking about in their domain here. So if you have a square root or something like that, right? You have the square root of like 2 or something like that. If you have square root of x, you obviously can't plug in any negative number in there, right? And so it's not going to be continuous for any negative number. But again, we're talking about the domain, right? And the domain will match the continuity for this. Again, just keep going here. Trig functions, exponential functions, log functions, and inverse trig. All within the domain, and so we can kind of just draw from what we already know about domain to continuity for all these functions. So this list right here is pretty much everything but piecewise functions, right? And so, because with piecewise functions, you can jump, okay? And so an example with a piecewise function is something like this, right? Here, let's say that this is like there's the xy axis, and these extend to infinity, right? This domain is for all x values, right? The domain of this function, but it's not continuous here, right? It gets broken up, and so continuity and domain is a very different thing. And a piecewise function is a great example of that, right? There's a jump discontinuity. Okay? So with that under our belt, we can do some practice with these theorems. Okay? And so an example here is, does the function g of x, which is sine of x over 2 plus cosine of x, have any discontinuities? Well, let's think about what we already know. Okay? Theorem 2 is going to help us with that. And I guess theorem 1 as well, right? Where we're going to combine both these theorems, right? So for this thing to be continuous, well, sine of x needs to be continuous, right? For everything. Cosine of x would need to be continuous for everything, right? And 2 plus cosine x needs to be continuous for everything. Let's see if that's true. Well, first thing to note, sine of x and cosine of x are continuous for all x values, right? And so that's a check. Number 2 is that, well, does this denominator ever go to 0, right? That would be the only other source of discontinuity that we would get. Well, let's think, what would make this denominator 0? Well, if cosine x was -2, that would give us a discontinuity, right? That would give us a denominator of 0. But the thing is, cosine of x, right? Cosine of x ranges from -1 to 1, right? It never will give you something that, like, just think about the graph of cosine x, right? It just oscillates back and forth between 1 and -1. It never goes to -2. And so the denominator is never going to be 0, okay? Because cosine of x can never be -2. And so that means that we're continuous everywhere. Okay, so let's write that down. Cosine of x can never be -2, and so denominator can never be 0, right? Okay, and just I do want to, I hope I'm not over explaining, but I do want to go back and understand, talk about why this makes sense, right? According to our theorems, sine of x and cosine of x, right? We know that we can just think of their domain, right? Their domain is all x values, right? And by this theorem too, right, we know that trig functions, they fall on this list, right? And so they are continuous everywhere in their domains. And pretty much theorem 2, you don't need to think about this entire list, just think of everything but piecewise functions. I think that's a little bit better to think about. Now we can combine them all like this, all in this gross manner, because of theorem 1, right? Because of how they can be combined. It's a combination of 1 and 5 here, okay? Right, we just need each piece to be continuous everywhere. And sine of x is continuous everywhere, cosine of x is continuous everywhere, and our denominator is going to never be 0. And so we know that, okay. So we can say, thus, there are no discontinuities. Okay, I just really wanted to hit home those theorems quick because we do have another example here. Actually, we have a couple more. Okay, which is good. So find where the function h of x is continuous. Okay, and so we need to again figure out, well, you know, where is each of these parts continuous, right? So let's look at natural log first, right? We can piece it. Natural log of x is going to be continuous in its domain, right? And where's its domain? Well, it is from not including 0, right? So that's not going to be including 0, but it goes up to infinity, right? But you can't get 0 or a negative number, and that's why we're not going to include that. That's why we have a parentheses, right? This is interval notation. Okay? Next, we can look at tangent inverse of x. That's the next piece on our list. Now, just for all of you that don't know, because I didn't know this until Calc 2, because we do inverse tan all the time in Calc 2, this is what inverse tangent looks like that. It asymptotes at pi over 2 and negative pi over 2. Okay? And so, but it is continuous for all x values. And so this is from negative infinity to infinity. Third, we need to look at x squared minus 1. Right? Is this continuous for all x values? Well, yeah, it's a polynomial, right? But the other thing that we need to look at is this ever 0? Right? Because we can't have our denominator be 0. And here you can see that there are two places where this x can be 0. You can solve this equation if you want, but you can see that if we have x equal to 1 or x equal to negative 1, well, that is going to be a problem, right? And so they can't equal, you know, that is basically what's not in this domain. Okay? That's what's going to make this thing discontinuous as well. Okay? So let's combine everything that we know now, right? What is restricting us from being of a continuity between negative infinity and infinity? Well, let's look. These aren't restricting us at all, right? They're from negative infinity to infinity. But what natural log of x says is that we can only be from 0 to infinity. Okay, cool. Let's get rid of that and write 0. Okay, great. But we have number 4 to worry about, right? We've already taken care of 1, 2, and 3. But for number 4, we need to remember that x can't be 1, x can't be negative 1. Negative 1 doesn't matter because that's not in our continuity domain, or not that, I'm not going to say that. It's not in our continuity interval, okay? Well, you know, so that doesn't matter. But x not being able to equal 1 is a problem, right? Because that's still in our interval right now. So what we're going to do is we're going to split this thing up at 1. And we do that by just putting a 1 there and putting a 1 in infinity. And to write, you know, it's this and this, we just write a little u for union. Yeah, that's how we write that. And so I am going to put that here. So it's all on the same page. That's what this like gray line is through here. All right. So moving on to, I think our last problem. Yeah, our last problem for the green section, and then we're going to move on. I think we have just a few more sections after that. And then you hopefully will have a very good grasp on continuity. Where is the following function continuous? Okay, so now we have a piecewise function that we're dealing with. And so what we got to do is see, well, how does a piecewise function differ from what we've already been doing? Right? Well, here's one thing. Remember how I said that with Theorem 2, right? With all these functions that are continuous in their domain, right? Well, that's not including a piecewise function, right? That it's literally every single type of function except for a piecewise function, because you can get those jumps. And so domain can differ from continuity. And so we have to check those gaps, right? And so you'll see that here. So the first thing that we want to do, right? we want to just, when I say check gaps, we want to check any point where we could get a jump. Okay? The only points, the only places where that can happen, and the continuity can differ from domain, is at the transition points, right? That's where we go from one function to another. Okay? And so that's just something we'll have to check. But first, I want to check what we do know, right? And that what we can see a little bit easier. And that is, well, are these following functions continuous? Well, 1 minus x squared is going to be continuous for everything, right? Because it's a polynomial. So it's going to be continuous on negative infinity to infinity. But what about natural log of x? Well, natural log of x is only continuous from 0 to infinity, right? And does that affect us here? Does that restrict us, the fact that it is from 0 to infinity? Well, how do we figure that out? Let's look at where it's being defined in the piecewise function. It's only for x greater than 1. So there is no restriction here because, from 1 to infinity is within where natural log of x is continuous, right? So we could say natural log of x is continuous from 0 to infinity, which works here, which works with our restriction. Okay, or domain restriction, whatever you want to say to make it mathematically sound. All right. Third, though, we want to check at x equals 1, because that's where we're transitioning from one function to another function, right? That's where we could have that gap, and therefore our domain wouldn't equal our continuity, right? So we need to see if that's continuous. Now, what is our condition for this thing to be continuous? Well, remember from the orange section, I believe. F of 1 needs to equal the limit as x approaches 1 of f of x. And remember, when we say that, we're talking about from both sides, right? And so we need it to be continuous from the left side and from the right side, right? So this all needs to be true. And so, we need to check both sides, because both sides are going to give you different functions, right? Because this is the split point. So first off, what is f of 1? That's probably the easiest one to do. Well, f of 1, this is the function that includes, right, 1 minus x squared is what includes x equals 1. And so it's 1 minus x squared, x is 1. And so this is 0. All right, awesome. Now what about the limit as x approaches 1 from the negative side of f of x? Well, what's the function from the left-hand side? It's 1 minus x squared, right? And so to find the limit as x approaches 1 from the negative side of 1 minus x squared, we can just plug in 1, right? Because this is a polynomial, it's continuous up until, it's continuous for everything, but it's continuous up until 1, and that's what really matters here, right? And so we can just plug this in, and of course we get the same exact thing we just got, okay? And that shouldn't surprise you. Then let's check the limit as x approaches 1 from the positive side, and this is going to be a little bit different, okay? This one, well, that's going to be the limit as x approaches 1 from the positive side of the natural log of x function, right? And for that, we can plug in again, natural log of 1, right? That's equal to 0. So what this means is that since these two limits agree with each other, right, that means that our overall limit exists, right? And so we can say that the limit as x approaches 1 of f of x equals 0, right? And so we could say that I need to make this like smaller because it's taking up way too much real estate on my page. I honestly wonder what the smallest is that I can write, and you guys are able to like see fine. I don't really think I want to test that though, or else I get angry people in the comments. Okay, so we could say that since 1 and 2, since these two things, right? Since 1 and 2 and f of 1 equals the limit as x approaches 1 of f of x, the function, or so we could say like f of x is continuous on negative infinity, negative infinity to infinity. It's continuous everywhere. We didn't have any points of discontinuity, right? And are we on the green? Yeah, we're on green section. So I'm going to circle that with green. Right? And so, yeah, I mean, the reasoning, I've shorthanded the crap out of this. But, the important part is that we saw that this is going to be continuous on its regular interval, and then the jump is what we need to care about too. We saw that that was continuous, and so the overall thing is going to be continuous everywhere, negative infinity to infinity. So moving on to continuity from the left or right. Now this is something that can actually trip up quite a few people. It's really just, it ends up being more like a one-sided limit, and that's pretty much what it is. But I'm going to show you what the continuity from left and right is using an example. Okay, and the example is going to be pretty much the same thing as what we just did. Okay, so find the x values where f is discontinuous. Okay, at these values, is f continuous from the left, from the right, or neither? So first off, let's identify where we have x values that give a discontinuous function, right? Well, let's think. The first thing I want to do is exactly what we did in the last time, right? We talked about just our functions in general and where they were continuous. We have 3 functions here, not 2, but we already know that x squared and x are continuous from negative infinity to infinity. And secondly, 1 over x is going to be continuous everywhere but x equals 0. Okay, that's going to be the only point of discontinuity, right? But we need to know, right, whenever you find a discontinuity, you got to see, well, is that in your restriction, right? Like, is that included in your piecewise function? No, it's not, right? This is x is greater than or equal to 1. That doesn't include x equals 0. Okay, so we could say, but that is not included here. Okay, now third, we need to check our first jump point, right? The first point where we switch from one function to the next, to make sure there's no jump and there's, again, no like jump discontinuity. Okay, that's going to happen between x squared and x, and that's at x equals negative 1. So is this thing continuous at x equals negative 1? Well, how do we find that out? We use the limit as x approaches negative 1, right? And that needs to equal the actual value at the actual value at negative 1. Okay? First, we'll write down the value at x equals negative 1. that is going to be what? Well, this is where we include -1, so that's x, right? And so we just substitute in for x, and if we do that, we get -1, right? This was this function was just x. If we plug in -1 for x, we get -1. Okay. Now that's also going to be the limit as x approaches -1 from the positive side, right? This will also equal -1. The reason why I say that is because, well, this is the function from the right-hand side. And if you want to, guys, if you want to draw a picture, like I didn't to start off this problem, but if you want to draw a picture and that makes it a little bit better, you can go ahead and graph your piecewise function, and it might make it a little easier to see this. Okay, here I just kind of want to keep on the pattern that we've been keeping with. But yeah, so x, you're going to have like an x squared here, and then an x, and then a 1 over x, right? And that's kind of the order of your graphs. I didn't line them up at all, but that's the point, okay? And so from the right-hand side, you are on that y equals x graph, okay? And so that's just going to hit the same exact point as the exact point, right? It's what we've talked about from before, okay? And so the limit would be the same. But the limit from the left-hand side, we got to see what that's going to be equal to. Right? And from the left-hand side, we're talking about x squared. Well, with x squared, we actually have to square the -1. Right? Because it's, that f of x ends up being x squared. So actually, I'll write it like this. I don't want to confuse people looking back at the PDF, so what I'll do is I'll write it like this. Right? So that ends up equaling 1. So here, we end up with a discontinuity. Why do we end up with a discontinuity? We end up with a discontinuity because 1 is not equal to -1. What we're going to end up getting is, well, from the left-hand side, we're going to approach 1, right? There'll be a, and this isn't going to be a straight line, but again, I'm just trying to make the concept go your guys' way. We're going to end up picking back up at -1, and then we're going to keep going, right? And actually, I believe that this is wrong. This is going to be an open circle. This is going to be closed, right? But that's the idea. Okay, there's going to be a jump there, and that's what we just discovered. Cool. So now, moving on, let's check for the other discontinuity, right? The other place where we could have one, where we jump over from x to 1 over x, right? We're looking at this gap now. Right, hopefully this drawing isn't the most confusing, right? I was just trying to show you the order of the graphs. Like this is an x squared, this is an x, and this is a 1 over x. Okay, so we're looking at this gap now. And we'll see if there's a discontinuity. Now, for that, for it to be continuous at x equals 1, the limit as x approaches 1 of f of x needs to equal f of 1. Let's find what f of 1 is. F of 1 is going to be found with this function, with the 1 over x function, because that's where we include 1. If we plug in 1 to 1 over x, we get 1. Okay? Cool. Moving on to the limits. We can see that the limit from the positive side of f of x, the positive one is going to be 1 over x, right? That's going to be the function from the right-hand side, right? And we can see that with this little cruddy graph here, okay? And so from the right-hand side, I mean, it's going to agree. However, from the left-hand side, now we're dealing with that x squared, right? We're dealing with x squared. And so we have to see, well, when we plug in 1 here, do we get 1 again? And that answer is yes. So now we can see that since the limit as x approaches 1 of f of x equals f of 1, right? And that's equal to 1. So, you know, that's a nice way to write that. F of x is continuous at x equals 1. I had like a little brain fart there. Okay, so that's something interesting to note. And so we only have a over this entire function, this entire piecewise function, the only place we have a discontinuity is at x equals -1. Okay, now this brings me, because that was only one part of the question, right? We were also asked, at these values, is f continuous from the left, from the right, or neither? And for this question, we need to refer to this chart. Okay, so f is going to be continuous from the left at x equals a if the limit from the left-hand side will agree with your point, right? Meaning that, let's say that your actual point is right here. Okay, let's say that that is your point. Well, let's say that the curve comes up and it agrees with your point, but it doesn't agree from the right-hand side, right? When you're coming in from the right, it doesn't match the point. This is called continuity from the left. Okay, because it's working with the left, it's not working with the right, because your actual point is here and not here. Now, similarly, you know, you could maybe draw me an example of something that's continuous from the right, right? That's when your right-hand limit equals your point. Okay, and so that would be when you have your point and it lines up with the curve from the right, but coming from the left, no sir, no sir. All right, and so you can also have neither, by the way. This is if you have your point here and your curve just completely just is like nope, and then just decides not to go there at all. That's when neither of your limits are going to equal the actual point, right? Because the limit from the left-hand side would point here, and the limit from the right-hand side would point here, and neither of them are pointing to your point, right? Neither of them are approaching your point. And so those are the different types of continuities. Okay. Now what do we have here, though? So looking at our one discontinuity, we had that, well, the limits from the positive side was equal to -1, and the point was equal to -1. Right? So these two things were equal. And so from the right-hand side, we equaled the point, and that means we were continuous from the right, but we were not continuous from the left, and that's why this thing is not continuous overall. So here we are continuous from the right. So f is continuous from the right at x equals -1. And we can circle that. By the way, I did notice earlier, I completely messed this up. This is not squared, but you still get 1 as your final answer. Our function was not x squared. It was x, right? That was the middle function, not x squared. So I'll like do some editing stuff with that, and I'll just like put a pop-up on the screen. Okay, that's future tense, or that's like, yeah, that's future tense for me and past tense for you because you already saw it. So all right, intermediate value theorem. So this theorem can definitely get wordy, right? When I read this theorem, it took me like 5 reads to even get an understanding of what was going on, and so I don't want that to be the same thing for you. Okay, it can get really overcomplicated. I just want to try to break this down for you. Okay, so we're going to say a couple things. Okay, first, let's say that f, right, this function, is going to be continuous from a to b. It's a closed interval, meaning that we have closed brackets, right? So we have like, we're including both endpoints. That's what closed interval means. So f is continuous on this interval. Okay? And we can just write a to b. Okay? This is somewhere where you have a continuous function that starts and it ends, or it's at least continuous on that point. Second, we have that n is any number between f of a and f of b. Right? So these are two y values. Okay, of this function. Okay, now, so showing a graph of what we just said, we could have some function, again, that looks like it starts at f of a and it goes to f of b, right? And we'll make this purple because we're in the purple section. Oop, missed that guy. Okay, and what the intermediate value theorem states is that you're going to, and again, n is any number between f of a and f of b. So this is all n, right? You're going to pass through all n's as you move from a to b. It doesn't matter how you draw f, it matters that f is continuous. That's the only thing it matters on. So you're going to pass through this entire range as you go from a to b, right? It's saying that, you can't have any, like, I'll draw from here to here. You can't have any ones where you, like, draw f and it doesn't go through all of n, right? It has to go through. The only way that you could do that is to break the whole continuity thing and do this, right? And now we haven't passed through, like, this stuff, right? And so that's an example that would break the intermediate value theorem, because now we have a function that's not continuous. But yeah, that's what the intermediate value theorem is. It means that we have all these intermediate values as we go from f of a to f of b, as we go from a to b on the x-axis. Okay, so that's what the intermediate value theorem is. Hopefully that makes sense. Now, and I did say down here, if we say this like math people, there's always going to exist a number c in that interval a to b, such that when you plug in c, you're going to get that number n. So let's say instead of being, let's go up here actually with this graph. Let's say that n is this point right here, right? Well, we can trace that over to a point on this graph, right? And that, let's say that x value is c, right? And so there's always going to be an x value along the interval where when you go up, you get n, which maybe this is another, value, right? So that's the whole point. Awesome. And I'll leave that as it was before. So, and I did say if f is discontinuous, we could break this rule. An example of that would be if we did a piecewise function with a jump. So I do have one example for us to go through here. Okay, and that's to show that a0 of the following function is between 1 and 2. Okay, between x equals 1 and x equals 2. So we have a polynomial here, and I just want to show you what we are about to do here. Okay, and I shouldn't have this equals 0 there. So if you understand the intermediate value theorem, this problem should actually be really nice. And even if you don't understand it fully, this problem will really help you too. So what we have here is a polynomial. And a polynomial is going to be continuous for all x values, right? It's completely continuous. There's no point at which the polynomial is going to stop. So what that means is that if we have some start 1 and some n2, right? So these are two x values, and we have two y points that straddle the x-axis, right? So they straddle the x-axis. What ends up happening is that when you draw that line in between them, right, no matter how you draw it, you could end up drawing it like this, right? It has to pass through the x-axis. And so if we can find that our f of 1 is positive and our f of 2 is negative, or maybe it's the, the opposite way, right? We know from the intermediate value theorem that at some point it has to pass the x-axis to get from this point to this point, to get from point A to point B, right? So that's what we're about to find out. Let's start by plugging in 1. If we do that, we get 4 times 1 cubed minus 6 times 1 squared plus 3 times 1 minus 2. This gives us 4 minus 6 plus 3 minus 2, which is -1. We do f of 2, right? And so if we have a 0 in between 1 and 2, f of 2 is going to have to be positive here, right? If we plug in 2, okay, we get, well, let's see, we get a 4 times 8 is 32, minus 6 times 2 squared, that is going to be a 24. 6, 2, and if we just do a little bit of subtraction here in addition, we get 8 plus 6, 14, minus 2 is 12. Okay, and so we could say by the intermediate value theorem, f contains a 0 in between 1 and 2. Okay, and that right there is our answer. Okay, again, let's understand why that happened, right? Because if you have, you know, your in between 1 and 2, you start out below the x-axis, which is what we did here. We start out at -1, we end up at 12. In between 1 and 2, somewhere, to get from negative to positive, we have to cross the x-axis, right? And so that's how we figured out we could get a 0. That's the intermediate value theorem. One of those intermediate values in between -1 and 12 has to be 0. Okay? So that's really, you know, what this problem was all about. All right, so that is going to do it for this video. Now, remember, I do have that full Calculus 1 course in the description down below, so if you're interested, I definitely recommend that you check it out. Basically, you know, I give you a bunch more practice problems that we get to go through together, and it's also a better opportunity for me to get to help you, you know, one-on-one. And, you know, that would be really, hopefully really helpful. Anyways, thanks for watching, and I'll see you soon.